Hey, so a few minutes ago in class, we were working on this problem right before my internet went out, and I wanted to finish it here, although I was going to use a slightly different method than we were using. So we were using either the integrating factor or the Euler-Lagrange method in order to find a particular solution. And right before the internet went out, we came across a problem that involved integration by parts, and so I also just uploaded a video that will talk about that method. And so you can get there that way. And actually, I'm going to trust you to finish that method and show you a slightly different way. And this is just a way of sort of helping think about these things. So if we can find a particular solution and a homogeneous solution, right, then we'd be done. And this one is a bit more complicated. It's not an obvious way of finding a particular solution, but I want to walk you through a little way of thinking about this, and sometimes this is helpful. So my desire is to get that t cubed. So that's my desire in blue. Over here I have a 2t, and I have y. Y has to be doing something. So, well, in order to get that t cubed, I'm going to first guess something like t squared over 2. Right? That would give me a t cubed. But the difficulty here is this derivative, right? So I would also have to include on this left-hand side the derivative of what's ever in there. So right now, the derivative of t squared over 2 would be 2t over 2. So here's the thought. Is there something I could stick in here that would go away? So by go away, I mean, is there something like a constant that I could stick in here by adding or subtracting that would somehow help me get rid of this? So that's a bit extra over our t cubed. So what's nice is there is this 2t out there. And so if I were to subtract off of this a 1/2 on the inside, that would, in this instance, introduce a, oh, what is that? What is that? Yes. It would introduce a 2t over 2. Why didn't I simplify that? That's why I was making a weird look. But it's negative 2t over 2. And that would actually cancel with this out here. And when I take the derivative, the negative 1/2 will go away. So with that thought, you might say, hey, well, maybe a particular solution will be t squared over 2 subtracting off 1/2. And in fact, that will be a particular solution. And so if you come across one in this sort of method just by sort of thinking about it and playing around with it, that's good enough. You don't, with that, I don't have to do the integrating factor method. I don't have to do Lagrange or Euler-Lagrange's method. I can just use this and then find the homogeneous solution. So I'm going to do that. So verify when you do either integrating factor or Euler-Lagrange, you will get this same particular solution or one that can be used, which will be very, very similar, but might look something like the homogeneous solution as well. So what is the homogeneous solution? Let's find it. So we need to solve, maybe do this in green, dy dt plus 2ty is equal to 0. So for this one, if you're looking for the homogeneous solution, we'll often we'll just do separation of variables. So dy divided by dt, so dy dt is equal to negative 2ty, and etc. So then we just solve this, finish up and say, so this is the integral of dy over y is equal to negative 2 integral of t dt, or you can write that whichever way is most convenient. So in this case, you end up with natural log of y is equal to negative t squared plus some sort of constant. So y is equal to e to the negative t squared plus c, but we have seen that this often can be reduced as another arbitrary constant. Maybe we'll call it k here. You could also just call it c. And so here is your homogeneous, put an H there, your homogeneous solution. So we use the homogeneous solution as well as the particular solution, and we stick them together to get our final solution. So let's actually zoom out a little bit so we can see both of them at the same time and say our general solution to this problem is y is equal to t squared over 2 minus 1/2 plus k e to the negative t squared. Great, so we're almost done. Very, very close. The only thing we're missing is that we were given an initial condition. So the initial condition says if I plug in a 1 for t, I will also have a 1 that comes out for y. So let's try that out. Initial condition, let's plug that in here. We'll do that in, say, the color white. So if I plug in a 1, I have 1/2 minus 1/2 plus k e to the negative 1. That better be equal to 1. Well, these kill each other, or they go away. So k would be equal to just e, right? So in this case, k is equal to e, or e to the positive 1, right? Or just e would be enough to get e times e to the negative 1 is equal to 1. So this then simplifies to our final solution, y is equal to t squared over 2 minus 1/2 plus, well, do I want to write it this way, times e to the negative t? I could, but there's a little bit nicer way than that to write it as just 1 minus t squared. And there you have it.